Hello, everyone. Thank you for having us here. We're here to present ICSGoat, a damn vulnerable ICS infrastructure. I'll just share some brief information about us. I'm Shantanu Kale. I'm the infrastructure lead at INE. I have published my research at Blackhat US, Asia Arsenal, DEFCON 30 demo labs, and multiple places. I've been a co-trainer in training at CSIS Goa, RootCon 16 and 17, with topics such as network testing, cloud testing, and AW attacking serverless applications. I've been a co-contributor to AWS Goat. I have strong roots in cloud interpretation testing, vulnerability scanning, and open source intelligence techniques. Along with me is Divyan N, the software engineer at INE. He's published his research at back at Asia Arsenal and has been a co-contributor to Azure Code and GCP Code. He's also been co-trainer in training at Seaside Score with strong roots in cloud and network security. These are the other conferences where our work has also been showcased. We work for INE, there's a premier provider of cloud and cybersecurity trainings. First of all, we'll go over the threatscape faced by ICS systems. Now, this is with respect to Kaspersky report. Now, as there was a rapid adoption of these information systems for organizations, it gave rise to multiple other challenges. Now, and these affected all the lower and middle level hardware these that were used by these information control systems. Now, the types of hardware included are stationary portable systems such as laptops, computers, and for operation by the engineering staff, the SCADA monitoring systems, the industrial routers, or the network interfaces that separate this control these networks, the PLCs, the programmable logic controllers, and at the end are the field devices that have a varying difference of complexity, which include like walls, switches, sensors, and they could have analog or digital input output. With all of these devices, there was also an additional cybersecurity challenges that accompanied them. As the complexity of these systems increased, the about different hardware devices and software components that are produced by multiple different vendors, and these are produced with minimal attention to security. So this definitely increased the risk of known and known vulnerabilities, as these were designed to ensure compliance with the CIA requirements. But due to device compatibility, these all systems were put at a very high security risk, and they were left in very highly vulnerable configurations. The safety configuration in a typical SCADA deployment for the field devices is not at all designed to perform well in the event of direct tampering with the control processes. Okay, so these devices are controlled by PLCs and the logic controllers. Now, if there's a tampering with the data that they receive from these components, there could be many other in multiple number of ways how this could be tampered with. Could be a malicious actor that has gained access to the network, or also an existing staff that has already does have access to the network. Now, in most of such cases, the systems cannot perform their functions properly. Thus, a disruption in these processes could cause serious damage. Now, 10 to 15 years ago, it was supposed that an air gap between this whole SCADA network and the control network and the outside system would be easy to implement. But as time goes on, these plants do also have a reliance on the modern finance, supply chain, and all the planning processes that all depend on connectivity. So this renders air gaps practically not possible. Very little chances that the solution can be used in the future. Now, this is how a threadscape would look like. Now, the attackers, they would we could separate the whole system plant into different networks. One could be the office network used by the employees for all the day-to-day tasks, operational management. Now, someone could gain access to these systems, use infected keys, or just be able to exploit some vulnerability and get into the network for some web server, anything at all. There's the plant DMZ network. Okay. Now, there could be bad access rules, the network configurations. SCADA stands for Supervisory Control and Data Acquisition. Now, these systems have a high-level overview of the machines that are being controlled, the PLC, the field bus, shows the data from the sensors, the PLCs, all of these things that interface with the plant machinery. Okay. Then comes the control network, where the actual programmable logic controllers, the PLCs, are present, which communicate with the field bus. If an attacker gains access to office network and then is able to get into the SCADA network, he will be able to view all of the field buses, all of the PLCs that are sending out information, and also be able to view a part of the information that the devices from the control network are sending to the HMI, that is part of the SCADA system. Now, if you are able to modify the PLC logic or send malicious data to the controllers, it will be disrupting the process. Moving on, what was the motivation behind creating ICS code? We have created labs on various ICS protocols such as Modbus, DNB3, MQTT, PCUA separately, but there was not a proper playground where you could see how all of these protocols come together in the form of a real world environment. So there was a lack of an expansive and realistic ICS pen testing environment, and that is what we aim to achieve with ICS Code. And always contribution from the open source community and security professional would help us make this into a better tool. Here we have ICS Code. Now, ICS Code, a damn vulnerable ICS infrastructure, mimics real-world ICS infrastructure, but has added vulnerabilities. Multiple popularly used protocols are simulated, as I mentioned earlier, such as MQTT, DNP3, Modbus, OPC-UA. This focus on a black box approach, and it will help you to understand possible threats to critical ICS infrastructure. These are the protocols being used: Modbus, DNP3, OPC-UA, and MQTT till now in ICS Code. Now, this is the ICS code infrastructure diagram. It is comprised of three main networks. First of all, the DMZ network that contains a web server, cloud storage, and a management server. The web server, as in part of a DMZ, is accessible from outside from the internet. The main network is isolated, houses all the actual systems, the PLCs, the walls, sensors, actuators that are used to control the whole manufacturing process. The whole scenario is of a pharmaceutical manufacturing company with all of these multiple sensors to perform processes such as starting from the raw material handling, the mixing and blending of the raw materials, the fermentation, the filtration and purification of those, the formulation, and finally the filling and packaging. So each of these steps are being controlled by multiple sensors along with walls, mixers, temperature monitors that are further controlled by PLCs. And this communication between the PLCs and all these sensors is happening with various different protocols. Then we have the HMI network that contains the SCADA system and HMI for viewing the data coming from these PLCs. Then what was the challenge with building a realistic ICS scenario? First of all, there was an availability of publicly available resources. We had to scour deep and wide to find resources to guide us into what we are properly building. Now, to get it working, it required modifications to some protocol libraries for it to work in a simulation. Now, to containerize the protocol simulations, the multiple protocols we use for multiple different purposes, containerizing them was a tough challenge. Now, and incorporating multiple of these protocols into a single scenario was also a challenge that we faced. Now, there was not an open source SCADA system to visualize all the data from all of these multiple protocols. So it required us to make a custom made SCADA and HMI system. These are the other, this is the Goat family, the other tools that we have for the previously created and showcased at Blackhat. Now, how the installation for ICSGoat will be. So it is hosted in the repository, github.com and labs ICSGoat. So only requirements are to have Docker Compose specifically on your system. It works on a Linux, it has been tested on a Linux or Windows machine. The commands to clone, you have to just clone it, clone the repository into the directory, and a simple Docker Compose up will build all the required images from the Docker files that are provided, the whole infrastructure running. And now I'll just give you a brief overview how the initial attack vector looks like. Now you have the DMZ network that hosts a web server. This web server is a site for the company. Here the company is Pharmatech. Now as an attacker, you would is vulnerable to a popular CVE. Now exploit the web server, you'll get some files that indicate the presence of and storage or self-hosted cloud storage that which is also vulnerable. Now, there you are able to find credentials to access the management server. Now, this management server is a part of the main network, thus is able to interface with the control systems and view the data from the HMI. This starts the actual ICS attacks for ICS Go. We'll just go over a demo video. This will showcase some of the attacks that can be done with ICSGoat.
Checking the network of compromised machine. Scanning all the networks attached with machine using Nmap. We can see that there are many machines in the network. We got a machine labeled with ICSGoat HMI with port 5000 open. Using curl to check what is hosted on that IP and port. It's a HTML page, having an image, multiple divs, and a script. Checking what's in the script. It is fetching some JSON from endpoint data. Getting the JSON from the endpoint. This is a data about the readings and values of multiple processes in the plant. Browsing the IP and port on terminal with the help of Browse. There is a value changing at the start of the figure. Again, getting the JSON data to check which value is changing with respect to JSON. There is process named raw_material_handling with protocol Modbus, where the value is changing. Check it again to confirm. Here we can see in another similar process with variable valve pump that is set to 0. Checking it again on the HMI web page. The valve is likely to be the next one after the changing value. Checking the value of the valve again in the JSON. Saving the current state of values to a JSON file. Using Nmap to scan for any device related to Modbus. Here we can find a device with similar raw processing handler hostname with a port 502 open. This port is generally used for Modbus protocol. Using Nmap's NSE script to find if the port 502 is actually used for Modbus. Here we can see a Modbus slave device with ID named Pharmatech. Trying to read the coils of Modbus by sending data using Netcat. Creating a bash script, which will modify the data on the first 10 coils of Modbus slave device. Making the script executable and then running the script to write the values on the coils. Browse the HMI again to check if writing the coils changed anything. Here you can see that the valve is now set to 1 and further processes also started with it. Now saving the current state of values to a different files to then compare with the first file. Compare both the JSON files, and you can see that the values with Modbus protocol is now changed and few other values are also added. These fields are with the process mixing and blending, and the protocol mentioned is OPC UA. Scan the network again using Nmap to find devices which may be using the OPC UA protocol. Here we can see device with a similar hostname for mixing and blending with the port 26543 open. The port 26543 is generally used for OPC UA protocol. Checking the Python version and if the Python module named asynqua is present on the compromised machine. Using this module we can interact with the OPC UA devices. Creating a Python code using asynqua module to read all the nodes and values from OPC UA device. Running the Python script and we can see OPC UA node named pharmatech and variables related to mixing and blending. As we got the nodes and variables, it means that this node accept anonymous requests. Create another script to write over the pressure sensors variable. The value we are writing for the pressure is 51 here. Run the script to write over the variable. We can also see the node IDs are the same. Use the browse to check the HMI and see if the variable was successfully modified. You can check that the value 51 is set up. Create another JSON file with current state of the values. Create another script which will change the bioreactor level and set the waste removal valve to false and bioreactor pH to 8. This will contaminate the medicine created in this plant. Run this script to modify the values. Check the HMI and see if our modified values are reflected. We can see that the values changed by us are not reflecting or may be reset by something. Scan the network again using Nmap. In the scan network, you can find a device with MQTT hostname and the port 1883 open. This port is used by MQTT protocol, which is a standards-based messaging protocol. Use the Mosquito sub to subscribe to the MQTT protocol topic. Run the OPC UA write script again to see if we got any message on the MQTT sub. We can see a message that the ideal conditions are not met and resetting the ideal values. The MQTT is sending the message of reset if conditions are not ideal. Creating an exploit for MQTT, which will flood it to make the device's memory full. So the MQTT protocol will be down. Run the exploit and start the attack on MQTT device. Try to connect to the MQTT sub again, it is not connecting. Use the Nmap scan on the IP again and it says the host seems down, which means out attack worked. Now running the OPC UA script again and see if we manage to write our values. Checking the HMI to confirm the values are modified. All the other values are changed, but the waste removal valve is not set to false. It seems it is being reset, as the ideal conditions are not met. To counter it, modify the script to write these values over and over again using a while loop. Run the modified script and check the HMI for changes. The flush is now set to 0, wait till the next process starts. Now new values are reflected for the next processes. There is a valve at the end which is set to false. Logically this valve is breaking the flow. We need to set it to true to open valve for altered medicine. Scanning the network to check what device or protocol is controlling the next processes. Here is a device with hostname filtration and purification, which seems to be next process. Port 20000 is open on this device, which is generally used for DNP3 protocol. Use DNP3 NSE script with Nmap to get more info on the DNP3 device. Here we got the source and destination address for the DNP3 device, which will be helpful to attack it. Now, let's formulate a write payload for this device. It is probably a binary output. Build different sections of write payload and calculate their CRC and attach it to payload. Creating a CRC calculator script. Creating and attaching the CRC for the payload. Attach the CRC and payload bits to create a finally payload to be sent to device. Use Netcat to send the payload to the device to write over the binary output. As per the response, it is modified. Check the HMI to verify if the value is modified or not. Run the write payload again and check the valve status. It was set to true and again reset to false. This is because our payload sent it to set for 100 milliseconds. Let's run this payload in loop to make this valve open all the time. creating a bash script to run this command after an interval of 1 second infinitely. Running the script and then checking the HMI if the valve is set to true all the time. After the valve is open all the time, next processes are now started. Scanning the network again to check the protocol and device for the next process. Here we will find another OPC UA device with hostname formulation. Update the OPC UA red script for this host. Run the updated script and nodes and variables are listed. Create new write script to modify the values of the temperature and humidity sensors. Modifying these values to check on which optimal values, so the filling of medicine starts. Get the JSON data and check the bottle count in filling and packaging. Check it again and see if the value of bottle count increased. Bottle count is increased from 80 to 88. This means, contaminated medicine are now filled into the bottles and our attack worked.
I hope that was a good demo. Now, what are the future plans with ICSGoat? Plan to work with the community to introduce more protocols to ICSGoat to be able to containerize them or have any modifications made in the libraries to be able to containerize them. Now, we also hope to utilize ICSGoat to create even more realistic scenarios with the help of industry professionals, uh, thus leveraging open source community. And we also want ICSGoat to coexist with other projects. Thank you. Thank you for having us. I hope this was a good presentation.